Hi, today I'm going to talk about this pyramid DC power supply. I bought it probably about 10 years ago, and I was using it for running some radios, typically 12 volt radios, which require a pretty powerful supply, even transmitters, things like that. And this particular unit is, I think, pretty popular in the ham circle and people who are into ham equipment for powering their transmitters and receivers and so on. When they are not in the car, for example, you can power it off this particular supply. It's basically fairly high current. As you can see, it goes up all the way up to 30 amps rated, and then the supply, the voltage side is from at around 6 volts to about 20 volts, but the actual practical range is probably a little over 8 or 9 volts up to 16 volts, I think. So this is fairly crude supply in the sense that the control is analog, and you'll need to adjust it using a meter to get an exact voltage. This meter is not particularly accurate, but it will do for rough indications. So internally there are two ranges where this operates, one in the low voltage range between around 6 volts to about 10 volts, and then above 10 volts it switches another extra transformer winding in the primary to increase the amount of current it can drive. So you'll hear that classical thunk when you switch the voltage above that range, and you'll hear that when I demonstrate this unit a little bit later on. There's a bunch of protection modes in this, from over voltage protection to short circuit protection, and also a buzzer which comes on when the voltage is in a fault situation, or when the voltage drops below 6 volts. This light comes on, and the beeper comes on as well. It also has a fan. The original design had a fan which would be running all the time, which was annoying to me, so I made some changes to that. The main thing I wanted to tell you about in this particular video was this: when I was using it about 3 or 4 years ago, it was in a very poor condition. I think it had been somewhat been abused in some sense, and when I went into it and did some debugging on it, I found there were some issues with how the thing was put together. So what happened was, when I was using this particular thing, its regulation was very poor to begin with. It would start dropping voltage fairly heavily when the current was increased. That means the output resistance was pretty poor in the final drive, and so or there was some poor connections or whatever in the power transistors coming out into the main outputs over here. And I was doing some testing, and during the process of testing it, I blew up the supply. I basically shorted the outputs, and then it didn't recover from that short, even though it's supposed to be able to protect itself from that kind of thing. So at that point I almost threw the thing out, and I decided I'm going to fix it. So this is one of my first projects that I worked on among all the different projects I've worked on so far. At that time I had very little equipment as well, and basic meters and just simple debug stuff, and not even a good scope. So anyway, this was my first repair, and so it has some sentimental value, I guess, and it's now working very well after all the changes I did and fixed it. So what I wanted to tell you in terms of what I did to improve it, besides the original specifications, was to add an extra digital panel over here, which is DC voltage and amps. So it kind of duplicates this, but it gives you a little bit more accuracy. I added a thermal switch for the fan, so if the temperature on the heatsink is not terribly high, the fan wouldn't come on. So if I'm drawing a light load, a few amps, maybe up to 4 or 5 amps for a while, it will basically run without the fan, no problem. One thing I found that in the process of debugging this thing was the thermal conductivity of the heatsink to the power transistors was pretty poor, and that could explain some of the poor performance that I was seeing in this particular unit. Other thing I did was to also add a 10 turn potentiometer here for controlling the voltage. The original design had a simple single turn potentiometer, which was very rough in the sense of actually setting the voltage. So now I've got a little bit better control on that. So that's the main thing. So besides the fixing of the unit after it basically was completely destroyed, I added these other few things that I just talked about to make the power supply work better and have some redundancy in terms of the meters and stuff like that, and reduce the noise level coming out of the fan. So here's the inside of it. I just took the top cover off, and there are 12 screws you remove, and that's basically exposes the whole thing. You can see in the middle of the whole power supply is this huge transformer. It's quite heavy. This whole thing is probably weighs 4 or 5 pounds, I think, at the minimum. This transformer is basically the down conversion of the 120 volts down to about 16 volts or so that drives the output voltage. And the fan is a different fan. The original fan was a little bit smaller. I put in a bigger fan, and also put in the thermal cutoff switch, which is hard to see in this particular thing, but it's mounted on the back of this heatsink on where the power transistors are. There are 4 power transistors, as you can see, 2N3055s, and they had very poor conductivity to the heatsink, and that was causing problems, and that could explain some of the failures as well. The main board is actually over here. You can see there's one control LDO kind of linear regulator, and that's the brains of this whole thing, and that drives the gate drives sorry, not the gate drives, the base driving of these 4 transistors, and there's another heatsink that's, I think, driving those output transistors, which is also one of the transistors that blew up. So among the things that failed was that controller IC, the SCR, the triac, which was on the output, also had blown up, which was to prevent the over voltage, which has a Zener diode based control circuit. And what else? The rectifiers were okay, I believe. There was no problem with that. And you can see that the main rectifier and the decoupling capacitors of the DC side, secondary side, are down there. You can see all the capacitors there. The capacitors survived the whole experience, so I didn't replace those. They were in good condition. And the rectifier, so you can see the rectifier down there, the multiple terminals on that, and bolted onto the chassis. And there's a fuse over here, and back over here you can see I put in the meter, and that meter connections are, I had to make a square rectangular hole for that, and that's seen right on the front over here. And that's basically it. Okay, there's a shunt on there, as you can see. That's a shunt. And yep, that's all as far as this thing is concerned. It's a very, of course, analog in all ways. It's got a lot of wires running all over the place, so it took me a little bit of time to find the right schematic and work on it and fix it. So pretty much took apart the whole thing when I did it. So, and also simulated the whole circuit in LT Spice, which was which was a learning experience for me as well at that time. So overall, I'm pretty happy with how it's performing right now. So before I go into some of the schematic and simulations and the components that failed, I will just do a brief demo of the unit itself working. So here's the setup of the power supply driving DC load. Currently it's turned off. Just no current is coming off of the power supply, and the voltage is 14.318 volts, which for the resolution on that meter is good enough, 14.3. So now I'm going to start increasing the load. It's going to be a constant current load That means the supply will just keep drawing current from the meter, and let's see how the voltage drops as the current increases. So that's basically our load regulation. So I'm going to start increasing the current slowly. So about 1.5 amps. 5 amps, 6, 7, so about 10 amps now, and you can see the voltage has dropped at 14.287 volts. It's not the greatest supply, but that's what it is. These are not precision supplies. Of course, it's drawing a decent amount of power now, almost 140 watts. If I can go all the way higher to around 20 amps maybe. So it's about 19 amps, and it's still 14.26. It's not dropped too badly. When I had the supply earlier, before I repaired it, this would have been down to like 13 volts or even lower. And right now it's actually doing a pretty good job at driving this large amount of current and still maintaining a decent output voltage at the source. And of course, depending on the cable resistance, the load might see a slightly lower voltage, but in current mode I'm just trying to see what current it will draw without getting the voltage dropping off too fast, too quickly. And let's go even higher. This I believe is rated to around 25 amps, I'm not sure, but we can go higher until the fan kicks in perhaps. So it's about 25 amps and is still producing, maintaining around 14.24 volts or so. So now the fan is still not on, as you can see. I'll move the camera to this side. The real noisemaker is the load, active load over here. This is getting warm, it's quite hot right now. The power transistors at the back, there are 4 of them. So it's drawing 25 amps at this point, 24.6. Meters 14.24, still maintaining that voltage fairly well. Shining a light on the fan to see a little bit better. Well, let's hope the fan does come on. So at this point it's putting out more than 300 watts I believe, and the voltage is very, very stable at 14.23 volts. For most of my own applications I would be not drawing more than 10 amps on this particular, from this supply, from what I actually use it for. Let's see if I can get a thermal camera and see what it's looking like inside. Because the cooling is not going to be very good even when it turns on, because everything is open here and the airflow is not really contained. So I'll turn it off as soon as the fan comes on, if it does at all. Still no fan, and voltage looks pretty decent, 14.22. It's dropped a little bit because the temperature, the heating effects of all these transistors thermally have changed their characteristics, but nothing has broken down yet. So I took the load off just now to see, check the temperature again. This is 14.3 with no load now, no current. As you can see, there's no current, but I've dropped to 14.23. It's about 70 millivolt drop for a 25 amp output, which is pretty decent for a very simple power supply like this. I'm going to do a thermal measurement now. So I'm back to the 25 amps output again. I'm not sure if you can see this, hard to see on my thermal setup here. I guess it's not focused very well. Unfortunately, I don't have a good way to view this, but the white portions are the hot portions, the black is the dark, is the cooler. The transformer is getting a bit warm, and the fan is the only cool spot here, and you can see the heatsink on the other side is white hot. Measuring the temperature on the transistor itself on the case, it's about 68 and increasing right now. I'm using one of the infrared guns and it's about 77 degrees, and that's fairly close to the temperature readout by the meter using the thermocouple type device. So I think it's still not quite hot enough to turn the fan on. I could have probably used a slightly lower temperature cutoff to not stress the transistors as much, but I rarely use it in this mode except to test it, so I'm not particularly concerned, but I hope it will actually turn on at some point. So the fan really never came on, and the temperature stabilized around 82 degrees Celsius on the heatsink. I think that's a bit too high. I think I may have, with the cover off, maybe it's not getting hot enough to trigger it. So I'm going to probably replace that switch with a slightly lower temperature cutoff. I think it's uncomfortably hot right now, way too hot to even handle. So I think this may not be good for the life of the supply. So maybe something around 60 degrees probably is safer. But anyway, otherwise, except for that, I think it's working fine. It didn't actually blow up or melt anything, so I'm pretty satisfied. I think next perhaps we can look at the schematic and see what we can figure out from what's going on inside. So right now the voltage has returned to 14.3 with no current. The whole thing is extremely hot. The transformer is hot. Heatsink is very hot. So I think that's plenty good demo for this particular instrument. It's not a precision supply, but it will drive easily 300 watts without any problems. I'm looking at the output voltage versus current and seeing the switchover point and so on the transformer's primary side. So right now it's about 7 amps of current, constant current I'm drawing from the Acme supply, load, I'm sorry, and I'm decreasing the voltage now. Let's see, it's below it's in a low voltage range right now, and the minimum is around 6 volts, I believe. It's not very linear, this, unfortunately, so you can actually change the resistance inside on the reference and make this change the range somewhat, but I haven't bothered to do that. So as you can see, it's about 6 volts, still drawing 7 amps. It's a constant current, and I'm going to increase the voltage back up. The current won't change because the load is maintaining that 7.2 amps or so, and is creeping up the voltage to 6.4, 6.5, 7, 7.6. Let's see, the cutoff is, should switch over soon. 8.5, 9, so I believe it switched over at the click I heard earlier. So now it's in the high range. You can go all the way up to 15.5 volts. And let's go back down again, see if I can hear the click. That's strange, I didn't hear anything. There, you can hear that click. Seems pretty silent. There you go. Yeah, you can hear a thunk. It's a very low frequency thunk. There. Unfortunately, with the load turned on, I can't hear it very well. So I'm going to turn off the load and just observe the noise now. Okay, now let's try hearing that sound. Okay, so it's in the low range hopefully now. There you go. That's the thunk sound. You clearly can hear it there. There. It's very clear now with this load turned off. Alright, so that's that. There's a relay in there that does that. The last thing now is when I turn off the supply, when it goes below 6, you'll hear audible sound as it discharges the cap below 6 volts or so. Nope. Oh, there you go. That's the sound there. Some protection comes on. Of the PS-26KX pyramid power supply, 12 volt power supply. To go over some of the schematic, let's start from the left side. So we have the main transformer, the power rectifier diodes, and a set of auxiliary half wave rectification for the supply for the IC, that for the linear regulator IC. And we have the fan, which is in this particular version is always on. You can see there's no switch here. And we have the large filtering caps over here, 6 of these 4700 microfarad 25 volt caps. So this output from this auxiliary board then enters basically drives the 12 volt regulator over here, the 7812 regulator IC, which provides 12 volts to all the chips and other circuitry on the board here. The 2N3055 transistors, power transistors, drive the unregulated output and to the final output over here, which is called Vout. The board that controls all the analog functions is the rest of the circuitry here that is shown on the schematic, starting with the IC, which is the main regulator IC, the LM723, and there's bias transistor for driving the base currents of these power transistors. This IC can at most supply around 150 milliamps, so we need a higher power driver, which is driven by this source follower, which drives the base of this transistor, the TIP41C, which can drive up to 6 amps, the output of which drives through a thermal switch into the bases of these 4 transistors. The feedback over here is for the current sensing on this chain of 3 resistors, which drives through pin number 2 and pin number 3, which is the output voltage, which if this voltage goes much lower than this voltage over here, which means that this voltage is basically driven hard, you would have this transistor turning on and pulling this base of this output transistor to ground, or to the output level, which basically turns off the drive for this IC. When this dies, this transistor will stop driving the base of this, and then the entire supply shuts down. So that's the current feedback. For the voltage feedback, we have this set of 3 resistors controlled by this variable potentiometer, which is on the front panel. That voltage is sensed over here, sent back to the error amplifier. There's a reference on chip through this current source, which maintains around 7 volts on pin number 6, and that voltage is divided down and provided as an error amplifier reference input. And besides that, there is output protection circuit. We have the SCR that senses an over voltage condition over here to prevent the voltage from going well over 15 or 16 volts. And once this triggers, this SCR can't be turned off, so you have to turn off the entire power supply, which then will reset the SCR. Besides that, there's an over voltage and under voltage sensing circuitry over here through this V out, which is sensed on this 2 resistor network here, divider, going through this amplifier, and then drives over voltage and under voltage sensing amplifiers. This has got a long time constant, this has got a short time constant. You can see by the feedback over here, and that drives a buzzer and an LED. So as long as the voltage remains within limits, this supply will not have any annunciation of these errors. In the case you have a SCR triggering, of course this voltage dies, the V out dies, and this buzzer will keep sounding until you turn off the supply. Over here is another amplifier which senses again the output. If it's the voltage of which is voltage divider output of this guy, these 2 resistors, that drives this amplifier, and it drives a relay which switches the transformer primary windings to, in case you need a higher voltage on the high range, this transformer will change the voltage coming out of here to a higher level. And a lower voltage requirement below 10 volts, this relay will turn off and switch to another winding on the transformer. Besides that, there's not much else here. Most of these are, this set of 4 op amps is LM324 chip, quad op amp chip. Got a high gain op amp, not very critical. This so I made a few changes, and one of the changes I made was to replace this single turn potentiometer with a 10 turn to get finer resolution on the voltage. I also fixed or cleaned up the thermal conductivity on this heatsink by taking off all these transistors and applying a liberal coat of thermal grease to improve the conductivity, which was one of the problems I thought in the initial implementation, where these transistors would not be evenly heating up and causing problems. The output voltage wasn't very stable or poorly regulated. So that fixed one of the problems, I think. The other problem was when I shorted this or was operating the amplifier in a weird mode, I think I destroyed the SCR, and the SCR output probably was ringing or something, which caused this IC to fail, this transistor to fail, the tip 41C, and one of these 2N3055s to fail. So a lot of problems were created when this supply shorted out, and it took me a little while to get all these fixed, and right now it's operating quite well. Besides that, one more change was the fan. As I mentioned, I put in a thermal switch in series with the fan. Right now it's set at a fairly high setting of 90 degrees Celsius, which I think is maybe too high. It will turn on if the case is closed. That is, in my demonstration I had the thing completely open, so I think there was some cooling through convection, I believe, which didn't allow this heatsink to go above around 80 degrees or so. So it needs to get to at least 90 to turn on, but that's probably a bit too high, I think, because that was very hot, I think, and there may be local hotspots which could be even higher. So I might replace it with like something like a 70-degree or something to make this fan come on earlier. Then the last thing I did was to add in digital output for the meter, for the voltmeter here. So basically sensing the same voltage here between V out and ground, and as well as to put in a current shunt, which I did on this negative going rail. So that added some extra precision in the measurement of the voltage and the current coming out of this amplifier, out of the power supply. Spice version of the schematic shown earlier from the printed manual. This is the simulatable version, of course, that I created. So again, on the left side on top, we have the AC to DC conversion, the transformer, the input supply 120 volts, RMS is 84 volts RMS, 85 volts RMS, the fan, the decoupling cap for 4700 microfarad times 6, the 12 volt output that drives some of the supervisory circuits in the bottom over here, and then we have the IC723, which is a linear regulator, the 4, 3 and 2 and 3055s right up here, the potentiometer to control the voltage, it's over here, and the meter voltage, the meter itself and the controlling resistor for that, to trim resistor, and then the current source, current meter and the shunt. That's the SCR along with the Zener diode that controls the gate of that to turn on. And this is some loading stuff that I put in to short the output or do some other measurements, changing the load and so on. Currently I have a current source load over here, which is set to 20, a variable which is I load, which is going to be swept across many volt values. The bottom here is the upper cutoff, sorry, the upper annunciation, which if it goes above, I think, certain voltage, it will buzz, create a buzzer sound as well as to light up an LED. Then the under voltage detector here, it's got a longer time constant, and this is the range switching, which enables through this transistor, turns on a relay, which then changes the winding on the primary side. Of course I don't have that simulated, but it's just to show that it actually is doing something. Besides that, we have the same all the pins of the IC are replicated here, the current sense and reference for the current sense. We have the feedback voltage, pin number 4, the reference voltage, which is 7 volts coming off here, and that's probably, and here's the base driving transistor tip 41C, and the snubber resistors, all of them are identical to the one in the actual instrument. So this was simulated, and this is the LM324, of course. That's the 4 op amps used in the actual circuit, in the actual instrument. So next we'll look at the simulation results, and I've highlighted some of the nodes like the VB driver, the VB plus, the VREG, which are the important nodes I want to observe. I'm going to go over some of these waveforms. Starting with the current, that the load itself is swept from 0, 5, 10, 15, 20 amps, and these are turned on at 20 milliseconds. If I didn't do that, I'd probably see some negative voltages when the thing is turned on, because this is not a very intelligent simulation where it controls all the nodes correctly when it's powered off. Anyway, and this is the output voltage on top, V out. You can see it's around 13.8, and for different load currents. And out here at the bottom are 3 of the input internal waveforms. One is for the VB plus, which is the bluish waveform here, which is the actual unregulated output that goes to the final output V out. it has to be higher than V out, otherwise it's going to show significant error in the voltage or dropout. VB driver is the base voltage of the 2N3055, and that increases as the current is increased. And that's when I can see as the Vreg starts to drop with the higher current being drawn, it will actually start to cause problems in the output voltage as the regulator itself is not able to regulate very well. And you can see on this last waveform over here where the voltage is dropped by around 200 millivolts. I think it's already not very good at 20 amps. In the actual instrument, I was seeing a much better performance, maybe because some of the internal voltages or actual transistors that I use were different from um, what is in the actual in the power supply, so they don't match 100%. But overall, you can see up to about 15 amps, the regulation here is excellent, barely 5 to 10 millivolts across all these currents. And so the main thing is that we can simulate this circuit and observe everything inside if we model this correctly or do the schematic and use the components that are appropriate for the simulation. Hopefully this power supply repair and demo was useful and informative. We'll see you next time. Thank you.